second KICP Colloquium of the year. And the second talk on cosmic microwave background, but we heard last week on the end of Legacy from Plump, and Brian is going to tell us about fundamental physics at the Simons Observatory. That's not being constructed, so we're going from what's been done to what's coming. And I'm very lucky to have Brian here. So let me say a few words about Brian. Brian did his undergraduate work at Case Western in physics, and I'm just bringing it out. Where's Brad? Brad, were you at Case Western?
This morning.
He was at Case Western this morning, okay. And then he went to graduate school at Brown. He worked with Peter Timby on polar. Now, polar was kind of the first polarization experiment after the late 60s and 70s, when polarization was the rage to look for our motion relative to CMB, and that, pan out. But then polarization became very exciting, and came to pilot experiments on that polar. Then he graduated and went from polar to polartron with Sarah Church, and to meet up with, I got that wrong. Brad. Peter Timby, I forgot to mention. With Peter Timby, right, where you were a graduate student, and Brad was an undergraduate.
Yeah.
Peter Timby.
I worked with Van McCann.
Sure. Then he went to Stanford with Sarah Church, and Sarah Church actually produced a lot of excellent postdocs, and Brad was a graduate student there. So you followed Brad.
That's right.
Around. And then he went to Caltech, and Brad didn't go to Caltech. But Brad came here, so we invited Brian to come here and give a talk. But after Caltech, we worked with Andrew Lang and started BICEP, which you've all heard about. He went to UCSD in 2004, worked on the polar and things, polar bear telescope, and with that has pushed for that to become the Simons array, which is essentially 3 polar bear telescopes. I don't know if we can say something about that today, maybe. And then most recently, in 2016, he's become the founding partner getting the Simons Observatory go. And those of you might remember that Brian was on the schedule to give a colloquium last year. So he's been very busy. He had to postpone that colloquium because they had twins. I think the day of the colloquium very fast. So anyway, welcome. I'm glad you came here with Brad.
Thank you very much, John. It's great to be here. Yeah, I was going to come out after my wife delivered the twins, but I figured I'd stay home a little bit and help her with the other 3 kids that we have. Yes, we have 5 children. My wife assures me that we're at least halfway done. We may be completely done, but we're at least halfway done. It's a pleasure to be here. It's great to be here with John and so many friends, old and new. And this is such a center of the universe. I decided to put a picture of the universe seen from space. Now, this is actually supposed to be a movie, but something happened to the movie, and it's not playing. So instead, I'll show you something that's a little bit nearer and closer to many of our hearts, which is, I claim in some sense, a precursor to a lot of the instrumentation we're building nowadays in the cosmic microwave background research. And I think I've also been assured that next week there will not be a talk about the CMB.
That's right.
Because if you keep extrapolating, that's still be the Keating Institute for Cosmic Microwave Background Studies. But I'm assured that's not the case. But anyway, north of here, I drove by on my way from Milwaukee, not too far from Yerkes, which I understand sadly is being decommissioned. But if you look at this instrument, this is sort of the cutting edge instrument, maybe the last great refracting telescope, until this modern era of BICEP and other projects, including the Simons Observatory, as I'll explain. And these devices, refractors, have always had a near and dear place in physicists' hearts, not just astronomers. So the first refractor, or the first person to ever use a refractor and anchor, was of course the maestro Galileo. And he was also the first person to really do what we consider fundamental physics. So he engaged in pursuits of what we call relativity now, not traveling near the speed of light, but the properties of relative motion, were some of his stock in trade. And of course, that's fundamental physics. And I'll be talking about applications of the CMB's light that we can use to probe fundamental physics using technology that there's no doubt in my mind Galileo would recognize instantaneously. So this is 410 years ago he was using this device. And he achieved no small amount of fame with this great instrument. Of course, he self-published Sidereus Nuncius, the Starry Messenger, without peer review. That's pretty cool. And it actually made him a small fortune. People talk about wanting to make a big fortune, but sometimes you start with, you want to make a small fortune, start with that first. And of course, I claim that this telescope, this small little telescope, was actually a lever. That's a big telescope. But this one, literally, in some sense, transformed and transplaced the center of the universe from being the Earth-centered cosmology of Ptolemy and Aristotle, all the way up to the more modern conception that we now know as the Copernican theory. Many students and many people are confused that perhaps Galileo proved the Copernican theory, but we don't really go about proving things. We more disprove things, and he had great success with that. For he showed that through this very simple book, I actually got to touch a first edition of it at Williams College about 3 weeks ago. My friend Jay Pasikoff owns several editions. I don't know how he does it on their salaries that they get paid. That's a private school too, I guess they do, all right? We in universities of California could never afford such a thing. But anyway, I was proud to wear my Simons Observatory logo while looking at these sketches that in some ways show Galileo's greatest genius, but I claim also show a little bit of what I call his biggest blunder. So we're all familiar with Einstein and his biggest blunder, the cosmological term, as he called it. But Galileo did amazing things, but he too was not immune from making certain cognitive bias-based blunders that I'm going to describe. The most famous of which was involving the moon, and that he disregarded the effect of the moon as the source of the Earth's tides. And he claimed that the Earth's tides were instead caused by the rotation of the Earth and the ocean around it, sloshing about as it orbited around the sun. So he was trying to prove the Copernican theory, or give more evidence to it, retrodict the explanation for the tide. And that is probably his biggest blunder. Historians of science might disagree with me, but that's probably his biggest blunder. Of course, we now know it's caused by the moon. But his biggest astronomical blunder involved this asterism here. So I ask you first, students, what is this? What is this? Is this a constellation? You guys are astronomers, so can anyone say if this is a constellation or not? Who says it's a constellation? No one with tenure may answer. No, I'm just kidding. You can all answer. This is not. This is an asterism, and it has a very special name. Of course, if you speak Japanese, you know it as Subaru. But it's actually called the Seven Sisters of the Pleiades, who, as everybody knows from first-year astronomy, were the nurses to Dionysus, who's the god of wine. It's a very important god, and these goddesses have very important functions to keep him well libated with wine. But it's actually, as I said, perhaps the source of Galileo's biggest astronomical blunder. So when I was reading that copy that Jay Pasikoff showed me, I actually came upon a description which Wikipedia helps me translate from the original Latin. And it says what Galileo thought when he observed through his telescope. And he made this sketch. And Edward Tufte, who's this sort of, I don't know how to describe him, he's sort of a philosopher of science. He calls Galileo the world's first and greatest data scientist, in that he was able to convey things through both art and science, the impressions that he felt when he observed through his telescope. And it's sort of unique. And I asked, again, another quiz. There'll be lots of interactions here today. Hope you don't mind. He depicts here, Galileo does, two different types of icons. He has these sort of stars of David, these open stars here, and he has these filled-in stars here. And I asked you, what do you think the difference is between those? Again, nobody with tenure, I don't want to embarrass anybody. Any guesses as to what is the difference between these filled-in stars and the open stars? Okay, nobody wants to venture a guess? Now I'll open it to other people. Yes? Go?
What do you see by eye?
So yes, that's exactly right. So he depicted the stars that were open. These are the stars that he could see without the aid of a telescope, which he called a spyglass. So over here, our perspectivum. And the stars that you couldn't see, he depicted as filled in. So he's conveying an impression that he had, also the brightness, the magnitude of the stars as physical symbols, but also he was making a scientific argument by way of these icons. The argument that he was making was that the entire Milky Way, as he says down here, what was observed by us, royal plural, we, is the nature or matter of the Milky Way itself, which with the aid of the spyglass may be observed so well that all the disputes that have so many generations vexed philosophers are destroyed by visible certainty, and we are liberated from their wordy arguments. I like it because he's making fun of philosophers, so we all do that. All physicists do like to make fun of philosophers. We feel we're so superior. But in reality, he's also making the argument that the Milky Way itself, in other words, the milkiness that you can see by eye, Galileo claimed, could be resolved into stars. So here's this nebula here, which we now call a nebula. They called it a nebula too, But he was making an argument that just as these stars seem to blend together to make a milkiness to the naked eye, his telescope was inadequate to resolve this nebulous glow into individual stars. But if he had a bigger telescope, he claimed he could do it. And he actually goes through and he emits the Orion Nebula, and he says you could do it with the Orion Nebula as well, which is one of the most, has almost four stars as compared to the Pleiades has several hundred total. So he's making an argument that, in my mind, is actually an incorrect argument, but it shows this example of something very pernicious, which is confirmation bias. He's saying by visibly seeing something, you can make a scientific argument. In other words, you can trust the eyes to be scientific instruments. So this I call confirmation bias, and nowadays we know Vesto Slipher, who of course provided much of the data that was used by Hubble and others to construct the eponymous Hubble's law, etc. Vesto Slipher took his same spectrograph that he had applied to these galaxies so beautifully and extended by Wendy's work and many others, and he applied it to the nebula, and purely to the nebula in the early 1900s. And he showed that the reflection, that this glow here had the exact same spectrum as that star, Merope. So he proved using spectroscopy that these particles here were not stars, they were actually tiny mirrors. And they could reflect the light from the star. And this is an example of what's called a reflection nebula. And that reflection nebula is made of iron and nickel and pure carbon, some say allotropic diamond form. So it's actually true that diamonds are in the sky, twinkle, twinkle, little star. And what Galileo did when he was not making so many blunders, of course he had some success, right, or else we wouldn't talk about him. A lot of that was kind of self-promoting and so forth, that he's obviously a fantastic intellect. He changed the notion of where we fit into the universe. And I claim with refractors today, we're trying to do the same kinds of things. But I couldn't help but point out what happened to Galileo after these phenomenal discoveries, which he was basically forbidden to make in right after the Siderius Nuncius in about 1910. He was ordered by Pope Urban, 1610, to make no more discussion of the so-called perjurious heliocentric model. And instead he was forced to really say that he would never teach it in public. Not only did he teach it in public, he used Roman, he used Italian to do his writing in the Dialogo. And that made it much more accessible to people that the Pope didn't want to be made aware of these discoveries. So anyway, at first he had great success. So here he is showing his telescope in the summer of 1609 to the Venetian Senate, and they offered to do something that no professor could turn down. They gave him instant tenure at University of Padua, which is pretty cool, and they doubled his startup request. So that's pretty nice, you can't beat that. Tenure and doubling of startup, all in one go. Now what did they care about? They didn't care about astronomy. They cared about seeing an enemy flotilla far off on the horizon. And so by using a telescope, a distance viewer, you could remove the stealthiness that distance previously afforded. And that was quite valuable militarily. And there's a great book now out by none other than my children's favorite astronomer, Neil deGrasse Tyson, in which the discussion is revolving around how the military and astronomy have sort of been these uneasy allies for centuries. And it starts back with Galileo. Well, what Galileo thought would happen is something like this. All authors aspire to this. He's going to do book signing, go on book tour. And he got some success after it. But of course, much worse things happened than getting writer's crown. And that was, of course, appearing in front of the Inquisition, essentially. So here he is in front of his friend, Pope Urban, and there's a guy here standing with a stick. And they forced him to curse his theory and say he would never teach it again. Of course, they allowed him to live not so far from one of his illegitimate daughters outside of Florence. So that was kind of nice. And he continued to do some astronomical discoveries, even while in prison, which is kind of inspirational if you think about it. But the notion that he started to inculcate in humanity was that the Earth was not the center of the universe. Now, you SPT people will like this diagram. There's no reason to show the northern hemisphere up. So I figured, why not show it as the South Pole facing up? Okay, as all of us in the proper hemisphere will recognize. So with Galileo's telescope, he went out this far, out to the stars, and then promptly thereafter, there was a question as to whether or not we no longer were the center of the solar system on Earth, but perhaps the solar system was the center of the galaxy. And Herschel did work that seemed to suggest that we were. And many of these things revolved around the imprint and the effect of dust on observations of distant objects. And I'll talk about that briefly, but it is quite fascinating how dust has really entered into all these cosmic stories that we've been telling ever since the first refracting telescope was used in cosmology 400 plus years ago. So nowadays we're going to focus, the rest of this talk is going to focus way out over here on the CMB. But I wanted to, because I know some of you may be beginning students, just to recapitulate, what is so important about polarization? You've probably heard about polarization, but why is it so important? The reason it's important is that polarization gives you extra information about the interaction between light and matter. It not only gives you information about the light source that is producing the signals that you're observing, it also tells you something about the matter that the light last interacted with. So here's a sketch from my book where I show light from an unpolarized source can become polarized upon reflection. In this case, it's off of, say, the Pacific Ocean or something like that. And the light that's originally 100% or 0% polarized becomes perhaps 100% or more than 0% polarized. And that's how your polarized sunglasses work. So the lesson is, when even unpolarized light begins its life, when it interacts with a dielectric or with a metal, it can become partially polarized. And in that context, here's what it looks like in San Diego. You'll see this a couple times because it's a little bit different. I'm trying to make an advertisement for undergrads to come visit us in San Diego, and the deadline is approaching soon. So you'll see that slide again. But there's a slide from my friend Wayne, way back in the last millennium. Actually, this one's from 2001, but it's from a paper called the Polarization Pursuer's Guide, or I forget actually what you called it, Wayne. But nevertheless, this paper came out in the middle of my graduate career, and it was really transformative that someone as erudite as Wayne and Martin White could produce a document that really laid out the pathway to make detections of the kind that astronomers are aspiring to do today. And it was really prescient in this, celebrating its 20th anniversary of this paper. But these animations show also that cosmic light can start off unpolarized and become polarized upon interaction with the famous primordial soup. And then we can observe that polarization, and it can come in 3 different types of varieties. The one that's perhaps most enticing and the last to be detected, and perhaps may not be detectable, but we're hoping that it will be detected, is so-called primordial B-mode polarization from tensor perturbations, aka gravitational waves in the early universe. This would be an astounding discovery in fundamental physics. It would revolutionize our understanding of matter and energy at the highest energies possible, perhaps the shortest or earliest times that could ever be measured. So it's become somewhat of the holy grail in our field, and the reason for that is not just that it would be an indirect detection of gravitational radiation, which of course is incredibly important, and a new window has been opened only recently with the LIGO experiment into fundamental physics from gravitational radiation. This would be an indirect detection of that, and it would perhaps shed light on this epoch that is so hidden from our view by time, distance, and energy that it would be revolutionary. I like to show this diagram. You guys probably all know this. If you look at the CMB now, what we're really trying to do, and this is very cartoon form, is take a picture of the universe was resulting from when the universe was about 10 trillion seconds old, which is about 500,000 years, and invert that image and understand what the universe was like a trillionth of a trillionth of a trillionth of a second after the Big Bang, the inflationary epoch, when the universe, perhaps quantum gravity effects were the dominant effects in the forces of nature. Now imagine trying to do this in biology. So imagine you had this, you're trying to figure out what did your primordial blastocyst look like. So, when I give this talk to elementary students, I can't use this, but this is the way that you looked 1,000 seconds after your parents had their own personal Big Bang, so to speak. This is a collection of about 200 human embryonic stem cells, and 1,000 seconds or so after conception, this is what you look like. Now imagine trying to discover what that looked like by looking at an image of the person today that it would become. So I got this from John. So now this would be impossible, right? John's 2 billion seconds, about 57, 58 years old probably. Now this is only an extrapolation factor of 2 million. This is 50 orders of magnitude. So clearly, we have a lot to prove. If we're going to make particle physicists, other physicists, trust that we can actually do this inverse problem and understand from relatively late time, extrapolated back 44 orders of magnitude more. It's a big challenge, but I think we're up to it. So the basic logic is that if inflation took place, and it took place at a high enough energy scale, it would have produced quantum fluctuations that result in so-called tensor perturbations or gravitational radiation. Those gravitons, if you like, have infinite lifetimes, just like the photon. And they could last, for example, up until the universe decoupled. So up until the time the CMB was produced, 400,000 years after the Big Bang. That will then induce a swirling, twisting pattern in the microwave background called curl mode polarization. And that signal is what we're hunting for with telescopes like BICEP, Simons Observatory, UCSD 3G, and many other fine products. So the state of the field right now is from our friend Lyman Page in Princeton. He's compiled sort of a list of all current experiments and limits on things and detections of the B-mode polarization power spectrum. Well, I just said that would be the holy grail if we could detect it. And it would, except that the holy grail, the holiest of holies, is down here. And this is the primordial spectrum that we're most interested in. Its peaks at about a 2-degree angular scale. The signal that we've detected, that SPT has detected, and other experiments have detected is a so-called gravitational lensing polarization signal that comes from a less primordial, certainly not primordial signal, gravitational lensing by dark matter in the universe, in the later universe. So it's very interesting, and we hope to do great science with it, as I'll describe, and as I'm sure you guys are aware keenly here. So we understand the temperature spectrum extremely well, thanks to experiments here and elsewhere, and the Planck recently released Planck satellite data that I'm sure you heard about last week. We understand the E-mode spectrum about as well as we did the temperature spectrum about 7 years ago. It's amazing how much progress we've made in just the last few years. I was told by one of the most eminent theorists around, a member of the National Academy, etc., to give up on my thesis project way back in the late 90s, because no one would ever detect polarization at all, let alone detect signals at the nanokelvin level. This is fraction, this is 1 microkelvin squared. If there's anything down here, in temperature units, physical units, is at the hundreds or tens of nanokelvin. Even at the South Pole, that's a low number. That's parts per billion of the background ambient temperature. So we've detected the so-called lens, gravitational lens E-modes, and now what we're really shooting after in many ways is to fully mine these spectra here and dig into the primordial spectrum that might reveal the presence of early gravitational radiation. So we founded in 2016 what we call a CMD supergroup, and that was made up of former competitors that became collaborators, and it was really nucleated by one person, that's Jim Simons, and I'll talk briefly about him in a minute. This slide's already out of date because Mark Devlin is the past spokesperson, so my turn is telling me all the different past and former and previous presidents of the APS. We don't have such august titles for our leadership. I'm the director, and currently Adrian Lee at UC Berkeley is the spokesperson, the person with most of the power. I just have to sign a lot of checks. But this is a group, the collaboration. This number keeps changing, so I have to type over it in different numbers. We have over 200 people working on this project on all different continents. As you can tell here, there's a list of collaborating institutions. We just released a forecast and science goal paper that was put out last month, or late August. And here's the author list here, and the title is Simons Observatory Science Goals and Forecasts. And as I said, the observatory was really nucleated by a designer, by Jim Simons, to sort of answer certain questions in his lifetime. So we're already funded to build the Simons Array, which is 3 copies of the Polar Bear telescope. I'll show just a picture of it, and I don't have time to talk about it. And during the 2015, Princeton held a workshop, and it was called The Future of the CMB at Age 50. You know, which is kind of ironic because the CMB is like 13 billion years old, but they call it CMB at 50. They really meant post-discovery when they were scooped out of discovering it by their friends at Bell Labs, Penzias and Wilson. And at that, Jim Simons was a trustee of the Institute for Advanced Study, and he said, "Well, Brian, why don't we go out for a hamburger?" So we went out for a hamburger, we started talking about what we could do in the future with the Simons Array and other projects, and he said, well, what would be the ultimate experiment to do? And I said, well, it'll be something with many telescopes, different scales, different detectors, and he got very interested. And then he said, well, how long will it take to do? And I said, it'll be, between 10 and 20 years if we get the right team. And he said, well, make it 10, or closer to 10. I said, that's a deal, but you gotta quit smoking anyway, because this guy is quite a smoker, and but I'm hoping he'll be around in the next decade. He's 80 years old, he comes to work every day, he's just a phenomenal person. His daughter and her husband have also started a foundation that supports the Simons Observatory, so they keep philanthropy in the family. Here's a collaboration meeting we had at UC San Diego last year, just a picture. And here's the site. This is where we're going to go. It's very different from the South Pole. Spent a lot of time at the South Pole. It's a phenomenal site. This is slightly more north. It's at south latitude, about 29 degrees, in the Atacama Desert. It's currently one of the highest observatories in the world. So in the foreground, you really see the experiments that comprise the original founding members of the Simons Observatory. And that's the UC San Diego and UC Berkeley-led Simons array of 3 telescopes, 2.5 meter diameter telescopes here, here, and here. And these are about to get first light. This one's been observing for 6 years, and we're going to put a new receiver on this one in the next couple of weeks. And then we're going to combine forces with the Atomic Cosmology Telescope, led by Suzanne Staggs, and then build a whole bunch of new hardware here. And I'll show you that part of the plateau where we're working really hard to lay out where we're going to put these phenomenal instruments. And so what I'm going to do is walk you through a little bit of the science of what we want to do with this future observatory. And I'm going to focus on one science topic in particular, pertinent to, actually 2. I'm going to focus on 2 aspects of fundamental physics that I'm most fascinated by, and that involves the search for so-called cosmic birefringence, which would be a rotation of polarization as it propagates throughout the universe. And the second is how early and how old a magnetic field can we detect in the universe. We know magnetic fields exist in people and planets, in the solar system, galaxies, and clusters. We've yet to see a magnetic field at truly cosmological significance. So I'll talk about that today as well. In some detail on some of the aspects of experimental physics that pertain to unraveling the fundamental physics questions that I'm most interested in. So we are trying to understand whether or not inflation took place. Some people, currently there is sort of another one of these great debates. The original great debate, which was Slifer and Shapley, Curtis and Shapley had 100 plus years ago, I believe, roughly around now 1920s, I think. That great debate was really whether or not the Milky Way is a galaxy and whether or not there are other galaxies. It's really before we understood the universe for sure was expanding, and certainly before we knew there was a Big Bang. So to call that the great debate, I think, diminishes the amount of debates that still are to come in this field of science. So what we're trying to do is really understand something which has overtones of that expansion of the universe versus static, steady-state universe, and that is the inflation model really has very few competitors in this landscape of theory, and it's caused some people to take umbrage that it's sort of dominating the field the way Apple dominates smartphone sales or something like that. In that it may be so dominant that people are afraid to suggest alternatives to it, for example. So there's really only a small class of alternative theories to inflation that people take seriously. I'm not going to talk about those, but I think it's kind of interesting that these great debates keep echoing throughout history, and currently we have one that's very reminiscent of the static or quasi-steady-state universe debates of the 1950s with Hoyle and versus people like Hoyle and Burbage versus Gamow and others. So the universe can tell us a lot of information by way of mining its information from the CMB, all the CMB information that these photons carry. In particular, they carry information about every single thing that they ricochet off during their 13.8 billion year lifetime. So that can include things like how the universe is evolving, whether or not its expansion rate is changing in a way that we could forecast into the future, decide whether or not the dark energy is a constant or cosmological constant, or whether it varies. These are questions we might be able to answer with these future CMB experiments. Then also there's everything that the universe can produce that's local to us. All the galaxies, in our case, galaxies are local at low redshift compared to the CMB at redshift of 1,000. And the energy and the density and the property of the universe changed so much in those intervening 13.8 billion years that it's actually remarkable to me that we can unravel information about things without, say, distance information from spectra and from things that, what we're looking at are really these photons that come with very basic characteristics, polarization, intensity, and some information about their color. And from that, we can learn a tremendous amount. I'm going to spend a little bit of time talking about galactic foregrounds, in particular polarized dust emission, again, echoing the effects that Galileo fell victim to. I'm a cosmologist, in my opinion. I've always been a little bit too cavalier about the effect of dust in the universe. And then I'm going to talk about how the future observations that complement the CMB, using optical telescope surveys of starlight polarization and other sources, can give us additional information about the galactic structure in the Milky Way. And that's really important, I think, to do in the future. And the concentration that's going to happen, thanks to the successive groups here and in other places that I collaborate with, we've learned how to build these telescopes. It's not like it's going to create some physics revolution to build the telescopes. We're at a point where we just need to build more of them. And we need to build them smart. But really, it's the devil's going to be in the details and how we understand all the systematic effects that can afflict these photons as they propagate across the universe. So I'll talk about these challenges in just a minute. And I'll talk about the approach that we're using. This is sort of the one-slide cartoon that encapsulates our main science goals. So I talked about why the inflationary epoch is so important, so interesting. We also will have information about late time galaxies, galaxy clusters, Simons Observatory effect, very well-trodden path here. And I'm going to talk, as I said, about two topics that are components of what I call fundamental physics, in addition to things like relativistic particles, their count, their masses. You know, we don't know the masses of 3 of the 17 elementary particles, and the CMD may be able to shed light on those. I won't talk about those, because I'm sure there are many opportunities for you to learn about that, but I do want to talk about these two topics here, so-called cosmic birefringence and primordial magnetic fields. Because these are two aspects of fundamental physics, as relative, or as important as relativity in some sense, in my opinion. And it actually is some really cute and rich physics left to explore. So as I said, we have this paper, you can get on the archive afterwards. So here's the state of affairs. I showed you a version of this slide. This is now just kind of breaking down by angular scale, inverse angular scale. So small scales are going over here. The whole sky is over here. The full moon is about here at 1/2 degree. And so these signals from gravitational lensing occur at about 3 arc minutes, or about 1/10 the diameter of the full moon. We're looking for signals from them, and actually the BB power spectrum doesn't tell you that much. It's interesting, it's a nice consistency check. As I said, it's at the nanokelvin, you know, hundreds or tens of nanokelvin. It's phenomenally challenging to do these experiments. But actually the BB power spectrum itself doesn't give you that much information. It's sort of a nice consistency check. It's important to do, and many groups, including this group here, have made fantastic progress there. Of course, BICEP announced detection of this signal, which also included a detection of the the gravitational lensing B-mode signal. One of the flaws in the original sort of conception about the way that we go after signals like this is that we measure things until we saw a signal, and then we go back and see what we saw. And I think that that's sort of, we move past that. BICEP is a tremendous increase in capability and is still a world leader in observational results and limits on this primordial spectrum, on these primordial gravitational waves, by a factor of about 10. It's just phenomenal how good a job BICEP did. And yet, it also paved the way for how we need to improve things in the future. If we truly want to make measurements of the kind that will convince your friendly neighborhood particle physicists that we astronomers know what we're talking about when we say we're plumbing the depths of the inflaton and we're telling them what the masses of elementary particles are, we damn well better be confident that we remove any and all other sources of contamination. So to make a leap from sort of where we are now with the best results extant in the form of BICEP and KEC, all the way down to the level of the most optimistic or upper limits that we have currently, it's going to require a tremendous increase in experimental capability. So this is sort of laying it out by scale. The intermediate region there will be tackled by the Simons Observatory employing 3 refracting telescopes. So back to the refracting telescope. And I claim basically all CMD telescopes are refractors at some level. Maybe they're catadioptrics if you're a fancy astronomer term, meaning that even the telescopes that use lenses, use mirrors, also use lenses. And so actually understanding the performance of these things is critically important, as important as it was to Galileo. You know, part of Galileo's secret sauce is that he was also a mathematician. So he understood lens-making formulae and things that were just black magic to the spectacle makers that were making these lenses before him. So these telescopes, these 3 telescopes in our initial configuration, I'm going to talk a little bit about them, what their science goals are. And then the big boy, the one that we're going to call Big Jim and Marilyn, after Marilyn and Jim Simons, is the 6-meter diameter telescope here, which has an interesting design and somewhat unusual by conventional astronomical standards. And I'll explain why we made choices in that realm as well. Here's a zoom in on one of the 3 refracting telescopes. They'll have about 0.4 meter diameter lenses, which is substantial. Not anywhere close to your piece, but nevertheless quite substantial. And these will operate in 6 different bands, and I'll explain why we need these different bands by way of a metaphor in just a bit. And so too, we'll also have 6 bands, 6 frequency bands with 2 frequency pixels. So each pixel will be sensitive to 2 polarizations, horizontal and vertical, and 2 different frequencies simultaneously. And that's a big technical challenge to accomplish inside of optics and constrained mechanically that we have here to actually accomplish both high purity and high fidelity spectral and polarimetric measurements. So that's a big challenge. So why do we go through the trouble of measuring different frequencies? The main reason is this enormous grain of dust. Okay, so again, you're going to keep hearing about dust in this talk. I'm obsessed with dust, not just because my 5 kids make a tremendous amount of it, but because I think it's the most overlooked and humbling of all substances. And none other than Gandhi agrees with me, as I'll show at the very end of the talk. So a grain of dust, this is in Quantum magazine after the BICEP results sort of were being hotly contested in 2014. It's hard to believe it was 4 years ago. And this came out around that time, exactly 4 years ago, more or less, to this day. And it was that these tiny grains of dust could have magnetic dipole moments, and they could get aligned by these pervasive magnetic fields that suffuse the Milky Way. And everything that we seem to see has magnetic fields in it. It's almost impossible to get rid of a magnetic field. And so we always knew there was a possibility in BICEP to have contamination of the kind that could produce a signal like that, which we observed. But we sort of overlooked it in a sense that we would go back and follow up if we did make a detection of it. And it was only by working hand in hand with the Planck experiment that we were actually able to get to the bottom line as to what was the source of the signal that we saw. It wasn't from primordial gravitational waves. It was most likely from a combination of dust and gravitational lensing. So what do we do next? Well, I showed you this image originally. Now we know kind of like everything is polluted. So it's not just Southern California smog, but the cosmos is polluted. And actually the grains of dust, I'm sure there are experts here, more expert than I am, but they're essentially grains of soot that are slightly magnetic. They might have iron inclusions in them. They might have nickel, cobalt, etc. And they can become magnetized, and therefore they can align if they have asymmetric dipole moments. They can become aligned in the Milky Way's magnetic field. Now, I don't want you to get the feeling that dust is all bad, because as the late, great Carl Sagan said, we're basically, this is the famous pale blue dot image. So for you young folks in the audience, on Valentine's Day 1990, Carl Sagan commanded the Voyager spacecraft to turn around, look at the Earth, and take what was then not known as a selfie. So it took a picture of the Earth, and the technology was such that the entire planet fit on 1 pixel of this Voyager imager. And there were some diffraction spikes because they didn't pay attention to their refracting telescope camera optics. They didn't have as high fidelity as we demand nowadays. And so there it is. So these are streaks of sunlight. And Carl Sagan wrote the pale blue dot. He said, we succeeded in taking that picture. And if you look at it, you see a dot. That's here, that's home, that's us. Every saint and sinner in the history of the species lived there on a mote of dust suspended in a sunbeam. So the lesson is, the planet is basically a giant ball of dust. Okay, so don't get too down on dust. Don't diss dust too much, because without it, we wouldn't be here. And Carl Sagan also said we have stardust flowing through our veins, all sorts of other poetic images and metaphors that he was wont to use. But nowadays, we have to contend with it. We have to deal with it. So we know the properties of the constraining dust can be further improved upon by taking multiple spectral measurements. Not the single frequency that we used on BICEP 2, which is at 150 gigahertz, which is very sensible because that's where the CMB peaks. So you want to do the measurement where the signal's the brightest. It's like you look for your keys underneath the street light, even though you might not have lost them there. So you do the experiment where the signal is brightest. That makes sense. What we found out later is that we really needed to have many other frequency channels to guard against the contaminating signals from our own galaxy. Most perniciously, as I keep talking, dust, but also from synchrotron radiation. Hence, we have low-frequency channels at 30 and 40 gigahertz. So we have high-frequency channels, low-frequency channels. Here's a plot adapted from Kogut, and it shows the different levels of contamination and sort of the bloodbath that we're trying to deal out here. We're contending with signals that are orders of magnitude higher. So now I think this is in microkelvin now, and you can see, this is in nanokelvin now, and you can see up to about 100 nanokelvin or so. That could be the most optimistic level of CMB primordial beam mode signal. So it's just an incredible technical challenge. We've made steady progress, and I think in one of the CMB-S4 books, we show basically if you extrapolate Moore's law, the CMB community is improving sensitivity at a rate faster than Moore's law, which is pretty amazing. Considering trillions of dollars have gone into semiconductor fabrication, and only hundreds of billion have gone into CMB. No, I'm just kidding. I wish that were the case. Maybe 100 million or something has gone into it. So we're located here, as I said, and what's interesting to me is that from this site, As I showed before, this is kind of the layout of the land. Ancient Incan astronomers used to observe. And they were interesting as I researched them. They, first of all, I always thought Incas were like thousands of years old. Turns out there are people that claim they're Incas today, which is kind of interesting. But from our site in the Atacama Desert, they would conduct observations. They wouldn't name the things that they saw in the sky after the stellar points of light that they saw. The thing that they were most interested in were the clouds of dust that actually we can't see from the northern hemisphere, but they named these constellations of dust, and they named them after living things. So this is the llama, and that's the umbilicus of the llama. So you could have you could be a zodiac sign. What's your sign? I'm the umbilicus. What are you? I'm a frog. But these constellations they made in contradistinction to the Milky Way, which they called a dead river. So it was these living creatures made of dust sipping out of this dead river and giving rise to their imaginations. Again, this is pre-Netflix. Okay, so they had to keep themselves busy. One of the hardest things about building this observatory is getting the site and configuring the site for operations, getting permissions. We have to have a lawyer, a Chilean lawyer, which is really fun. And we have to communicate with governmental officials. We have to get diplomatic status of various people on the observatory so that I can park wherever I want, including in front of the fire hydrant. No, I won't be able to do that. But this site, this is perhaps one of the biggest challenges and should not be underestimated by our future upcoming collaboration, CMBS4. So you see sort of the layout of the land. We're basically building an outpost, not unlike a small version of the South Pole, just for this experiment to observe with. And then we have to observe for 5 years at a minimum. So here's the big telescope, Jim in Maryland. And this telescope has a primary and secondary mirrors 6 meters in diameter each. It's kind of an unusual diagram. So light comes in from the universe, bounces off here, goes into this cryostat here. I like to show this, always next to my graduate student Darcy modeled for this. So this image is the person. So when the graduate students are bad, you know where they're going to be. They're going to be confined. No, they won't do that. Please don't let anyone think that. So currently we have space for 13 of these optics tubes. They can have dual channel pixels in each one. And this whole thing is capable of having about 40,000 detectors in its first incarnation. It could have almost 80,000 detectors if we filled out all 13 spaces for this optics tube, or for optics tubes in this instrument. So it's a massive cryostat cooled to 0.1 Kelvin, 100 millikelvin, using dilution refrigeration, which I saw a bunch of them downstairs in the basement. Maybe they'll let you guys use them too. There's a cross section, again, for scale, there's a person. Could fit easily inside of there, comfortably inside of there. All sorts of refracting telescopes buried within this enormous reflecting telescope with 2 6-meter diameter mirrors. Just phenomenal in terms of engineering. Now, in this group I saw downstairs, in Brad and John's labs, etc., I saw graduate students working on machinery. It's probably built in your machine shop. We are not building this in anybody's machine shop. We simply can't afford to for a variety of reasons. Plus, one of my senior colleagues once told me, never do anything once. In other words, if you're going to wire an electrical outlet in your house, you only do that once. You should hire a professional to do that for you, right? The risks are simply too high. So we're probably only going to build one of these. We only have money to build one of these, and we only can fill out about 2/3 of its number of optics channels that it can contain. So we're going to contracting into a company called Diamondback outside of Boston to do this work. And each one of them will have tubes that we will make these optics tubes in labs around the world, in Japan, in Berkeley, and in Pennsylvania. And sort of a cross-section through it. I won't get into too much detail about it. You can ask me later how it works. The main thing is that it's 100 millikelvin. It has a massive number of detectors. This one system will have almost as many detectors that have ever been deployed cumulatively in the CMB industry, in the CMB field, which is just phenomenal. And it's really hoping to pave a pathway for the CMB Stage 4 experiment, which will build upon this, perhaps adding more telescopes of this size. Small telescopes are much more compact. My student looks a lot bigger, more imposing here when you compare her to this cryostat. So this is a pure refracting telescope. Also at 100 millikelvin and also using multiple frequencies, 6 different frequencies across 3 different telescopes. And this doesn't have individual tubes. This has just wafers that are illuminated by these 3 different lenses here. We have 2 different types of detectors fabricated, some similar to SPT3G, so-called sinuous antenna coupled detectors. This is the antenna. Each one of these antennae fit beneath one of these little hyperhemispherical lenslets. And then this is made at UC Berkeley. And these detectors are going to be made at NIST, and these are horn-coupled orthomode transducer detectors that have been used by the ACPOL collaboration. We'll put them in a universal focal place. Everything has to be, even though the detectors will come from 2 different foundries, they'll be compatible with all the downstream electronics, cryogens, mechanicals, etc. We're going to read out so-called MUMUX. I'm not going to get into this. This is an ambitious way of reading out thousands of detectors off of just 2 wires, because you don't want to go through all this trouble to pump. Imagine vacuuming out a chamber that's 2.6 meters in diameter, how long that will take, just the square footage inside of it, if you will. So we don't want to have a lot of wires and heat load going into it, so we are actually by necessity using what's called this micro multiplexing devices here that are being developed for high energy particle physics at SLAC. So we're kind of benefiting from a lot of engineering by Kent Irwin's crew. Okay, I'm going to move quickly now into the last few minutes to talk about, so you can see there are papers on our website. I want to close with this interesting science that I'm hoping to do alongside my colleagues in the Simons Observatory, and that is to make use of the essential fact of the photon. That photons have these 3 different main properties: intensity, spectrum, and polarization. And of those 3 properties, polarization orientation seems the most robust. In other words, if a photon starts out with a given polarization, it can scatter, but it will maintain that polarization. It's very hard to get photons to rotate their polarization. So we make use of that fact. And I like to point out that actually our eyes can detect color, obviously. Our eyes can detect intensity. Our eyes can also detect polarization. And I call it our 6th sense, just like my favorite movie. Okay? And it's this phenomenon I'm going to demonstrate here. Hopefully the screen works. So there's Bruce Willis. So this phenomenon called Haydinger's brush. It's a feature of your eye, that your eye has a molecule within the retina, in the macula, that has what's called dichroism. So it has a slight amount of preferential transmission for one polarization state versus another. That means your eye will see this pattern because the screen is polarized. I have my glasses somewhere, but I'm sure you guys can verify the screen is polarized. And so I'm going to take away instantaneously this color pattern, and you tell me if you see it persist. And if you do, you have more sensitivity to this Haydinger's brush, this macular pigment. So I'm going to take it away. It's going to happen instantaneously right now. Sometimes I see the complementary picture of it. I see the inverse. I see what was green turning to blue. One more time. So I'm going to take it away now. Anybody see the inverse cross pattern? Okay, good. So that's a feature that shows your eye is actually slightly polarized. Now, many animals have this phenomenon. What I want to use it for is to connect back to our patron, Jim Simons, which is a feature that he invented in mathematics called the Chern-Simons invariant, which is a topological invariant of certain shapes and forms, characteristic forms. No matter for that, while Sean Carroll was here, I think it was before he was here, in the early 90s, he asked the question, what happens if you add a term to electromagnetism that allowed a little bit of the electric field to be coupled to the magnetic field? Just pure electromagnetism, adding a forbidden term, which would allow the E field to have some component parallel, if you will, to the B field. And he goes through the math in this famous paper from the 1990s, and he shows that what will happen is that 2 different polarization helicities will travel at different speeds. And that will accrue over cosmic distances to produce what's called cosmic birefringence. So you have a rotation of the plane of polarization. Look here. The electric field is oscillating vertically here. It goes through, say, calcite or something that has birefringent properties, and it comes out rotated by 45 degrees. More rotation, the longer the optical path length is, and the stronger this coupling is. Coupling is a feature of the dielectric. So what would that happen? Well, we actually know what would happen. I claim this would be even, and this actually breaks Lorentz invariance. It singles out a preferred direction in space about which these polarization vectors rotate. I think that's kind of cool. It means that you show that Lorentz invariance is violated on cosmic scales at least. In fact, it made such great a splash that when it was detected in the late 1990s, anyone remember this? Front page of the New York Times. I love to show front page of the New York Times because the same people are still in the news. Like Newt Gingrich, this is 21 years ago. He's still in the news. Netanyahu, he's still in the news, right? I mean, this is like a constant of nature that, the Israelis and Palestinians won't be able to get along so well. But down here it says, this side up may apply to the universe after all. And what it was by looking at distant radio galaxies, this team showed that the plane of polarization got rotated by a substantial amount. And it turned out that although Sean Carroll had been the one to predict this effect, he actually went back and showed that they had made a statistical blunder in this claim. And it made, as I said, it made front page news. Now, in case you think it's kind of crazy, I'll point out there's an author in the audience down here who talks about effects related to polarization rotation. And that'll be my next topic. It's called primordial magnetism. And the bounds on primordial magnetic fields are what I want to talk about next. These are references that I can share with you about how you can get polarization rotation. But just to finish up, on a field of fundamental physics, as my title suggests, we don't know much about truly primordial magnetic fields. So in Coleman-Turner, it's discussed what would happen if you had a magnetic field of a given strength. And it could be ruled out by certain constraints on DDN, as the two authors can confirm. But in fact, we actually have no constraints on scales larger than galaxy clusters of a truly intrinsically formed primordial magnetic field. And what would happen if there was a field such as that present at the time the CMB was created? You'd get Faraday rotation. So you'd get a rotation of the plane of polarization by a small amount, exactly as Michael Faraday showed in the 1800s. This is pretty cool, and it's a way of having a window into the extremely early universe. Because how do you get magnetic fields that are so ubiquitous? We see them in galaxy clusters, we see them in individual galaxies, that is, people have it, birds have it, right? So how do we have it? There must be some original starting spark, some seed that was planted to then get spun up to make magnetic fields such as the ones we see. The arguments for why they exist are so intriguing, they actually provide a lower limit. So experimental physicists love lower limits. It means you're guaranteed to detect something. We have a lower limit on the mass of the neutrino. That's why we spend so much time, money, and energy on S4 and other projects looking for the mass of the neutrino. We know it exists, and we know it's within experimental capabilities. Here, there's a lower limit set. In other words, the primordial magnetic field must be greater than what I call a tenth of a micro nanogalaxy. Okay, it's a very small magnetic field. It's gotten from this mechanism here. I'll just breeze through it. When you look at a TeV blazar, when it interacts with the CMB and what's called the extragalactic background light, it should produce a halo. So when you look at these blazars, you should see a ring of fire surrounding them, a ring of light in the gamma ring, the absence of which implies that during pair production, the positron and electron went their separate ways. What caused that? A magnetic field at high redshift. So this is the argument that those authors used to set this micro-nanogas limit. We, with Polar Bear about 4 years ago now, set a limit of about under 4 nanogas. So more than 10 million times too high than the lower limit, but it's suggested, and it's interesting, and I think we should spend time looking at it. I'm going to finish up, because I know we're running a little bit late on time, this question of how you actually measure CMB polarization orientation is very difficult. It's very hard to calibrate polarization orientation. There's no, what I call, standard spaghetti stick. There's no source in the sky, like with Jupiter, when we calibrated a Polar Bear. We calibrated comparing how many photons we see per second compared to Jupiter. So we know Jupiter, we've been to Jupiter, we stuck a thermometer in Jupiter, not really, but we know its physical temperature, we know its size, we know how far away it is. We have an absolute calibration for CMB temperature. We don't have an absolute calibration standard for polarization. So we've attempted to make some. We came up with a technique I call self-calibration 6 years ago. We tried to use big telescopes and sources, as I know I was speaking to Tyler today, that he used on SDT pole. Very difficult to do this. And actually the level of uncertainty that you have in systematics is about 10 times bigger than the statistical horsepower of these experiments. We're in the exact opposite realm that we'd like to be in. You always want your systematic errors to be much lower than your statistical errors, right? Because otherwise you're dominated by measuring systematics. So here you have to do a very accurate measurement. You need a source of known orientation. And so we proposed, along with Brad Johnson at Columbia, we proposed building a satellite that would look out, not out, but look down. Unusual for a CMB-related satellite. This was unfortunately summarily rejected many times. So now we're looking at building a balloon, which we call Cal Zeppelin, to fly over the Atacama Desert in the far field for you aficionados, broadcasting a uniform 100% polarized signal in many different colors so we can calibrate the orientation angle of CMB photons. That's a very difficult challenge to do that. So that's the way we want to do it. I'll close with the timeline of the Simons Observatory, where we're going to do these, in my mind, incredibly exciting observations, followed hopefully by even more precise and more accurate measurements by the CMB Stage 4 experiment, which I'm sure you've heard about. Here's just a view of what we can see from the site in the Atacama Desert and what we're going to be looking for. And I promised you I'd close with two things. One will be a shameless ad for undergraduates to come to UCSD. But first, a moment with Gandhi, nominated for the Nobel Prize 13 times, number one. And actually, Hitler was nominated once at least. But Gandhi said, the seeker after truth should be humbler than the dust. The world crushes dust under its feet, but the seeker after truth should so humble himself that even dust could crush him. Only then, and not until then, will he have a glimpse of truth. And I like this as an experimentalist because he wrote a book called The Story of My Experiments with Truth. So we hear a lot about, kind of bending the truth falsely. He was a truth experimentalist of the most high sort. So I want to close with a plug. This is what San Diego looks like right now. It's being beamed live. No, it doesn't, but most 90% of the time we do have weather like this. Encourage you to apply, graduate students for postdocs, undergraduates for graduate school, etc. And faculty. Thank you very much.
Thank you, Brian. Questions for Brian? On your balloon source, whatever it was called, how's that? What are you actually using for the source?
Yeah, so we're going to have synthesizers. So we've sketched out a couple of filter banks and synthesizers that we could get, Virginia diodes, make some ones like this. It doesn't have to be powered. I mean, it doesn't need solar panels. You can actually run tethers to it, and then you have an extension cord that plugs into it. You can put it on a mountain way out over here, say, measure it. We can tether it, yeah. We've also used a drum down there. We've taken some video as well.
Question? Tom?
Is there a material difference between an asterism and a constellation?
Yes, so the Big Dipper is an asterism. It is not a constellation. That's sort of a colloquial term for it. I mean, I defer to my senior, kind of colleagues and more knowledgeable astronomers than I'm just a humble physicist. Yeah, that's what I've heard, is that it's basically a collection of stars in a colloquial name for that.
Just kind of a straightforward question. Just what value are do you expect to constrain?
With the Simons Observatory, so the target?
Not the array.
Oh.
Yeah,
The Simons array? Oh, the Simons array, yeah. So that, our limit is about 0.0, I have to look back. It's sort of at the 0.01 level with Simons array at about 3 sigma and after foreground cleaning. Yeah, so about a 7 times improvement over where we're at now. We're using 7 times more detectors, so given the same amount of time, it's not impossible.
And then follow it out then for Simons Observatory. What's the expect?
So it's about 3 times better than that. Yeah. And so it would be comparable to these other experiments that are targeting sort of the lowest achievable pre-stage 4, CME stage 4 experiments.
Right?
So this is kind of a big picture question about the Big Joe Maryland telescope. So all the other telescopes you showed have similar kind of design features, a big ground shield, and the telescope is silent,
Yeah.
well separated from each other. Is that one, when you go to build, it's sort of enclosed by this tight-fitting box,
Yeah.
which people have avoided since home to them, right?
Right.
So can you give some rationale for that?
Yeah, so it is a good question. So this telescope is not seeking the primordial D modes. So its science targets are factors of 10 higher at a minimum. It could be hundreds in some cases. So we're looking we're looking for clusters. We're looking for E-mode polarization signals. We're looking for some neutrino signals that will manifest themselves in the TE correlation function. So this has much looser, requiring to be a little bit, but the main reason is that it's exactly a copy, more or less, of what's called CKAP Prime telescope that Cornell is building. So exact same optical folded, very compact Hasse grain design. We're getting it built by the same company, and they give us a bulk discount, basically. So it'll be a lot cheaper. The design process was way far ahead. It meets all our needs. You can always do perfect, but this we think is good enough.
So you're not as worried about the side load part because of the...
Yeah, and actually, we are under illuminating. We have a lot of cold stops. We're actually worried more about, well, what happens if this thing sees the sun? You have because we are doing daytime observations, so we're going to pay to make the mirror surface worse than you get naturally out of the shop. So there are some features, but this thing's a 15-meter tall building. It's pretty impressive. The whole building's going to rotate. But yes, we don't need ground screens on this. We certainly need them on the small telescopes.
having two different detector architectures?
Time and money and risk reduction. So neither foundry could build all 80,000 detectors by themselves in the time scale that we need to get tested, quality control, because you don't want to ship down, you know, a broken egg to the table, right? So we have a lot of quality control, so it's going to be parallelized, and that's one way we can do it. And both groups have had good success building these types of detectors. It'd be funny if we made, you know, one group build the other one's kind of detectors. That'd be kind of Freaky Friday, but that's not going to happen.
Other questions? Okay, well, before we thank Brian again, just to remind the students, for everyone without a PhD to come forward and spend time with Brian while the rest of us go drink wine and trees.
Save some for us.
Anyway, thank you very much.
Thank you.